Okay, let's just get started then. So it's my pleasure to introduce Abdul Zalloum from Queen's University, and he's going to tell us about why hyperplanes are beyond cat-zero cube complexes.
Okay, so thank you for the invitation. And okay, before I start, I should say that everything I will talk about is in collaboration with Harry, Petyt, and Petyt and Spriano. And their names are here. Okay, so let me just quickly, so what's the story here? So the story is that, so hyperplanes is the main object, is the main tool for working with cat-zero cube complexes. And what I would like to show you today is that hyperplanes do arise very naturally in so many other spaces, including hyperbolic groups, hierarchical hyperbolic groups, and cat-zero spaces. But the main application I will focus on is the following. So one of the things you can do with hyperplanes is you can build something like a hyperbolic graph via hyperplanes and the way they intersect with each other. You can build hyperbolic graphs like the contact graph of Hagen or the separation graph of Genevious. So you build, something like the curve complex, where if you have a group of isometries that acts on the cat-zero cube complex, then it immediately acts on the corresponding hyperbolic graph. And the main application for the existence of hyperplanes beyond cat-zero cube complexes is that you can do that. You can take such hyperplanes and you can build hyperbolic graphs out of them. And the main space that I'm going to focus on today is cat-zero, is the class of cat-zero spaces. So we're going to define some hyperplanes for cat-zero spaces, and from the hyperplanes we will build some hyperbolic spaces where any cat-zero group will act on. So that's the plan. Okay, so very quickly I'll just remind you of what a cat-zero space is. So a cat-zero space is a space where if you give me any points x, y, and z in the cat-zero space, all right, and you look at the geodesic triangle connecting such points, and then you go to R2 and you build a triangle with the exact same side length. So you just go to R2 and you build a triangle, R2 triangle with the exact same side lengths, right? So if this had side 1, this will have side, length 1, length 2, length 2. So you build something with the exact same side lengths. And being cat-zero just says that if you pick a point here and a point here, and you look at this distance, and then you look at the corresponding distances, then you have to have this inequality. So if you have a point P and a point Q, and you look at the corresponding points P prime and Q prime, then the distance between P and Q is smaller than or equal to the distance between P prime and Q prime. That's what the cat-zero space is. Okay. Okay. So let's make the following definition. Suppose you have a geodesic metric space, and suppose you have a geodesic gamma. I'm going to be thinking of a geodesic ray, perhaps, or a geodesic line. Okay. So let's take some geodesic line. We're going to say that this geodesic line is decontracting if for any ball disjoint from the line, its nearest point projection to the line has diameter at most d. Okay, so you take any ball that you want, small or large, doesn't matter. As long as it's disjoint from the line, we want its projection, its nearest point projection, to have diameter at most d. That's what it means for a geodesic ray or line to be decontracting. Okay, so this is the picture we just discussed. Well, if you're thinking of something like R2 or Z plus D, you won't see any such contracting geodesic rays because there aren't any. So if you take, if you take a ray in R2, right, or maybe a line in R2, and then you take larger and larger balls, the projection of these balls is going to be twice their diameter, and that's not bounded by any constant. So no geodesic rays are going to be decontracting in R2. But if you look at something like maybe F2, and you take maybe the line, which is x, 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 and you take a disjoint ball, so maybe you take this ball here of radius, take it of any radius you want, as long as it remains disjoint, the projection of this ball to this line is going to have diameter 0. There is only one way to project. You have to do this, right? So every line in F2 is 0 contracting, while, as we saw, no line in R2 is contracting for any constants d. Now, there are examples in between. I mean, you know, if you look at something like, you take maybe a torus with a circle, and then you look at the universal cover of that, the universal cover of that will have a very particular look. The torus is going to give you a flat, but then the circle is going to give you a line sticking out of each grid point in the flat. So you're going to get something like a tree of flats. Okay. And the point of this example is that you see both sorts of geodesic rays. So you see, if you give me a geodesic ray which is entirely stuck on this plane, it's not going to be decontracting because you can take larger and larger balls and project them to it. But if you take some geodesic ray that spins maybe one time here, goes up, one time here goes up, and then one time and it goes up, then you can convince yourself that that geodesic ray is going to be decontracting, where the d is the maximal time it has spent in a flat, right? The largest projection you can get on such a geodesic comes from the largest time you spend in such a flat. So that's the idea. That's the definition of a contracting geodesic. It's something that does not exist in flats, but yeah. Okay, so let's go to cat zero cube complexes. Someone has a question or a remark or something? Okay, so let's go to cat zero cube complexes. So a cube complex is really just a cell complex obtained by gluing Euclidean cubes isometrically along faces. So what that means is that you just start with Euclidean cubes and you glue them isometrically along faces. So that's what a cube complex is. A cube complex is said to be cat zero if it satisfies the cat zero condition we mentioned 2 minutes ago. Now, this is not my favorite definition of a cat zero cube complex, but it's the one that's most. You can define cat zero cube complexes in a slightly more combinatorial way than I just did, but this is more consistent with the talk, so I'll stick to that. Okay, so that's what a cat zero cube complex is. Now, so as we just discussed, you have Euclidean cubes in cat zero cube complexes. Now, give me a Euclidean cube, a mid cube. So if you give me, maybe we'll first do an example. If you give me a Euclidean cube, something that looks like maybe a square, a Euclidean square, then you can define a mid cube. And a mid cube is, you just restrict one of the coordinates of the cube to half, and that's what a mid cube is. So this square here, it does have two mid cubes. It has this mid cube that comes from restricting this coordinate to half, but it also has this mid cube that comes from restricting this coordinate to half. So that's what a mid cube is. Anytime you have a cube, if you have an n cube, you're going to have n different mid cubes in it. Okay, so here is a picture of a cat zero cube complex. All right, and here is a mid cube. So I have a mid cube here. All right, so that's a mid cube. A hyperplane is what you get by starting from a mid cube and then extending it. You start with a mid cube, and whenever your mid cube touches an adjacent mid cube, you take the union of that and you keep iterating. So in this example, I have this mid cube here. Okay, but this mid cube, it touches this other mid cube in the adjacent cube, and it touches this other mid cube in the adjacent cube, and it touches this other mid cube in the adjacent cube, and you just keep iterating the process. You look at this point here and you ask, does it touch any mid cube in an adjacent cube? And it does touch this one. So you just continue and you're done. So that's what we call a hyperplane. So a hyperplane by definition is the following. You start with a mid cube, and whenever your mid cube touches an adjacent mid cube, you take the union of that and you keep iterating. So maybe we'll just see another example. So I have this mid cube and it touches this. So I adjoin them, it touches this, etc. So you get a hyperplane. Okay, so that's what a hyperplane is. You should think of it as something that splits the space into two pieces. It cuts your space into half. Now, anytime you have a hyperplane, as you see in this picture, this hyperplane, it cuts your space into two pieces. One, maybe I'll call the hyperplane H. I'm going to call this side H plus and this side H minus. H plus for things that live on this side, H minus that for things that live on this side. If you have a point X that lives on one side and a point Y that lives on another side, we will say that the hyperplane H separates X and Y. So just to say that H separates X and Y just means that X lives on one side and Y lives on another side. And this is not special to points X and Y. You can just take any set you want. You can take a set A that lives on this side and a set B that lives on this side. And you say H separates A and B. Okay.
Sorry, I have a question. So is it always the case that a hyperplane separates the space into two pieces? So for instance,
that's right. It always separates the space into two pieces. And the
what if you have a cube complex which has fundamental group, like a circle, you have cubes connected like a circle, and then you find a hyperplane which does not separate? Or
no, you don't. I mean, circles are not cat zero. So what I'm thinking of, so the way I define cat zero cube complexes is you have a cube complex, okay, and you also want it to be cat zero. So if you have something,
yeah, sure. Oh, I see. Okay.
So in particular, it's contractible.
Okay.
Okay.
Yes.
Okay. Okay. So right. So we do set. Okay. So something else that I want to define now that we have the separation picture, a chain of hyperplanes. So to say that H1, H2, H3 up to Hn form a chain. So H1 up to Hn form a chain if Hi separates. So if Hi separates Hi minus 1 from Hi plus 1. Okay, so in this picture, so what's a chain of hyperplanes in this picture? Well, you have this hyperplane. So if you maybe look at this, if you look at these hyperplanes here, then they form a chain because each one of them, if you look at this hyperplane, it separates this from this. And if you look at this hyperplane, it separates this from this, etc. So that's what a chain of hyperplanes is. Okay, so it's if you had to guess what a chain of hyperplanes is, you'd guess the right thing. It's a collection of hyperplanes which are where each one in the middle separates the one preceding it and the one that comes after it. Okay. Okay, so that's what we just discussed, separation and chains. All right, so there is a very influential theorem due to Sageev, which says that if you want to understand anything about cat zero cube complexes, it suffices to understand hyperplanes and the way they interact with one another. And there is a way to make this precise, and it really precisely says this. It says, if you know which hyperplanes intersect which, if I don't tell you anything about the cat zero cube complex, I just give you the combinatorial data of the hyperplanes, and I tell you which ones intersect which, then you can entirely recover the cat zero cube complex. Now, instead of making this theorem precise, I will give you a few examples to show you how it actually works. The distance is something you would like to understand in a metric space, and the distance between 2 points in a cat zero cube complex. And when I say the distance, I'm looking at the combinatorial distance, by which I mean I force myself to be stuck with the edges. I can't leave to the 2 skeleton or a larger skeleton. So that's what I mean by the combinatorial or the L1 distance. So maybe we'll go back to the plane example. You could look at maybe the combinatorial distance between this point and this point here. And the combinatorial distance is, well, 1, 2, 3, 4. but that's precisely the number of hyperplanes that separate these 2 points. Well, you have this hyperplane separating them, and you have this hyperplane, you have this hyperplane, you have this hyperplane. That's it, right? So the distance between any 2 points in a cat-0 cube complex is the number of hyperplanes that separate them. That's one indication that hyperplanes control the geometry of a cat-0 cube complex. But I'm going to give you many more examples. I'll give you at least 3 or 4 more examples. So let's see. So what else? Okay, so let's look at the following definition, and this definition will be useful for us. It'll come up often. 2 hyperplanes are said to be k-separated. So I hand you 2 hyperplanes, and we're going to say that these 2 hyperplanes are k-separated if the largest chain of hyperplanes meeting them both has cardinality k. So if you look at the hyperplanes meeting both, and you look at the largest chain you can form by hyperplanes meeting both, that has to have cardinality at most k. It's best to look at examples. So let's see some examples. So give me 2 disjoint hyperplanes, maybe this one here and this one. And this is R2. So I don't have the full R2 in the picture, but you can it continues forever. And I would like to ask, are these 2 hyperplanes k-separated? They're not k-separated for any k, because there are infinitely many there is an infinite chain of hyperplanes that intersects both, right? You can just keep going. The red hyperplane keeps going here, and you can find infinitely many things that cross both. So no 2 hyperplanes in R2 are k-separated. However, if you look at H2, if you look at something like H2, maybe let's zoom in. So I drew 2 hyperplanes here. The first one is this hyperplane, and you just keep going, right? Yeah. And then the second one is this hyperplane here. Now, if you ask, what's the largest chain of hyperplanes that meet these 2 hyperplanes? Well, there is only one hyperplane that meets both, right? There is only this hyperplane here that meets both, and that's it. So these 2 hyperplanes are 1 separated. The largest chain of you have a much stronger property than even a chain. There is only 1 hyperplane that separates both. So what's the moral of the story? The moral of the story is that this notion of separation, it's a hyperbolic-like thing, because as we saw, we did not see we separated hyperplanes in R2, but if you look at H2, every pair of disjoint hyperplanes are going to be 1 separated, or maybe 2 separated to be safe, but I think 1 works here. Anyway, so this notion of separation, it describes being, it seems to be related to hyperbolicity, and in fact, maybe I'll skip this. In fact, it's more. So the statement is precise. In other words, I hand you a cat-0 cube complex, and you don't know whether it's hyperbolic or not. This theorem tells you that the cat-0 cube complex is hyperbolic if and only if there exists a k where any 2 disjoint hyperplanes are k-separated for that k. Okay? So if you have a cat-0 cube complex, one of the things you would like to detect is whether it's a hyperbolic cube complex or not. And this theorem here, it tells you that you can detect whether it's hyperbolic or not purely via the geometry of hyperplanes, right? You look at every pair of hyperplanes. If they all happen to be uniformly k-separated for the same k, then your cube complex is hyperbolic. I'll actually give you a proof for how this works, because it's cute, and it shows you how arguments in cube complexes just really reduce down to combinatorics. So suppose you have a cube complex and you know that any pair of hyperplanes are k-separated, and you would like to show that your cat-0 cube complex is hyperbolic. Well, how do we show that the cube complex is hyperbolic? You take a triangle, x, y, z, perhaps. All right. And then if you want to show it's hyperbolic, you have to show that this side lives in the union of the other 2, right? That's what we have to show. You have to show it for every side, but without loss of generality. let's show that this side here lives in the other two. Well, the way to do it, well, you say, let's look at the hyperplanes. Let's look at the hyperplanes that cross YZ, right? The hyperplanes that cross YZ, they will either leave from this side or they will leave from this side. Okay. And then what were we after? What we were after is showing that this side here lives in the union of the other two. So pick a random point on this side. So let's pick a random point on this side. Maybe I'll pick this point here. And I would like to show that this point lives in the union of the other two sides. Namely, I'm going to actually show that this point is close to this point here. Well, how would you do that? You look at the, you want to bound the distance between these 2 points, right? So maybe you look at the geodesic, connecting them. You want to bound the distance between them, right? And the distance between them is the number of hyperplanes that separate them, right? And any hyperplane that separate them, it essentially will have to you know, the idea is that the fact that these two hyperplanes here are k separated, it bounds how many hyperplanes can separate these 2 points by k. Now you have to be slightly, you know, you have to do a couple more things, but that's the idea. The idea is that if you have a hyperplane that separates these 2 points, then it will have to meet, it'll have to meet these 2 hyperplanes, and that shows you that the distance between these two points is at most k. So knowing something about separate, you know, what we did here, we exploited the fact that any pair of the fact that any pair of hyperplanes are separated, it really just says that there is some sort of a narrow path that goes between them. So that's the idea of the proof. Okay, good. Any questions? Okay, now we discussed the notion of a contracting geodesic earlier. And that notion is interesting for so many reasons. Maybe I don't have time to get to now. But a theorem due Charney, Sultan, and Genevious in slightly different contexts, it shows that a geodesic ray is decontracting, okay, if and only if it crosses infinitely many k-separated hyperplanes at a uniform rate. So you have a geodesic ray, and the theorem tells you that it's decontracting if and only if you encounter, if and only if you encounter infinitely many pairs of these separated hyperplanes, where how separated is uniform, they're all L separated for the same L, and you encounter them at a uniform time, okay? So each time 3, you encounter a pair of 3 separated hyperplanes, all right? And that characterizes being contracting. And why am I mentioning this? The reason I'm mentioning this is because, again, here is another notion of interests, the notion of decontracting, and this notion can be described purely in terms of hyperplanes. Okay. Now, as we discussed in the beginning of the talk, if you have a geometric action of a group G on a K0 cube complex, one thing you would like to do, you would like to build a hyperbolic space out of your cube complex so that your group G acts on. You want something like the curve graph, right? You have the mapping class group acting, acting on itself, and what you would like some hyperbolic space that sees this action. You want a space that kills off all the products that look in all the products that live in your cube complex, and you want your group G to act on isometrically. So that's the idea. So you have suppose you have a geometric action of a group on a K0 cube complex. There is a way to build a hyperbolic space where your group acts nicely. Okay, there are many ways to do that, but I'll describe the one that's most consistent with what I'm going to speak about. So fix a constant L that's either 0 or larger. And this L is going to be allowed to change in a second. But for now, just fix it. So fix a constant L and define the following space. So take XL and DL. So I have my K0 cube complex X, and I'm going to define a space out of it as follows. The space XL is simply the collection of vertices in X. So I just take the vertices in X. That's my XL. And I'm going to give it the following distance. The L distance between 2 points is, well, you say this. The combinatorial distance between 2 vertices is the number of hyperplanes that separate them. Here you say, well, instead of counting all the hyperplanes that separate them, I'm going to count the hyperbolic-like ones, i.e., instead of counting all hyperplanes separating X and Y, I'm going to only count the pairwise L-separated hyperplanes separating X and Y. And that's a very reasonable thing to do because, as we saw before, L-separated hyperplanes are intimately connected to hyperbolicity. So what you're doing here is like, you're taking 2 vertices and you're saying, okay, the honest cat-zero distance is every hyperplane that separates them. So what you do is you say, well, the ones that are not K-separated, i.e. the ones that are not hyperbolic, I'm not going to count them. All right. So that's what this is doing. You just count the largest cardinality of pairwise L-separated hyperplanes that separate them. And I should say this is due to Genevious. And he proves that this space is it's a quasi-geodesic space. Any 2 points are connected via a uniform quality quasi-geodesic. The set as a set, it's your cube complex. It's as a set, it's the same cube complex. You just gave it a different distance. And I think the distance is very smart because you really just do the obvious thing and it works. The obvious thing is to just ignore the non-hyperbolic hyperplanes and magically it works. Actually, yeah. So he proves that it's a quasi-geodesic metric space and it's hyperbolic. Now, one of the very nice things about this definition is that anytime you define a distance, it's usually hard to check that it actually gives you a distance. But this definite, checking that this is a distance is immediate. Why is it immediate? You take 3 points, X, Y, Z. The first 2 conditions of the metric are immediate. You want to check the third condition. That's the main thing to be checked. Namely, you want to check that the L distance between X and Z is smaller than the L distance between XY plus YZ. All right. Now, checking the L distance between X and Z means you want to look at the L separated hyperplanes that separate X and Z. But any L separated hyperplane separating X and Z, they will either leave from here or they will leave from here. So any L separated hyperplanes that contribute to the distance between X and Z must either contribute to the distance between. So again, the picture is that if you have hyperplanes that are L separated, they must either leave from here or they'll leave from here. So if something contributes to the distance between X and Z, it'll immediately contribute to the distance between X and Y or Y and Z. And I think the philosophy of this is very nice because it tells you that anytime you have a cat-zero cube complex and you're interested in a collection of hyperplanes, they may not need to be the L separated hyperplanes. Maybe you would like to look at hyperplanes that has property blah. You can define a distance in the exact same way by declaring the distance between 2 points to be the collection of hyperplanes that satisfy a property blah. And then any hyperplane satisfying property blah that separates X and Z will either go from here or it will go from here. So this is something that I don't know if it's something you can exploit in other contexts. But I thought this idea was nice. And something you can see from this definition immediately is that if you have a hyperbolic cat-zero cube complex, then this DL that you define, it coincides with the actual metric. Because the actual metric counts all hyperplanes, but you're hyperbolic. So all hyperplanes are pairwise L separated. That's one of the theorem we mentioned. Anyway, so that's the plan. So what's the summary? So the summary is that I mentioned that there is this theorem of Sageev that tells you can understand anything about cat-zero cube complex via hyperplanes, and we saw some examples. The first example we saw is that distances can be described purely via hyperplanes. The second example we saw is that constructing geodesics, or they're also called Morse geodesics, if you know those better. Morse geodesics are also characterized via hyperplanes. Whether a cat-zero cube complex is hyperbolic or not is also characterized via hyperplanes. Namely, it's hyperbolic if and only if every pair of disjoint hyperplanes are k-separated. And finally, we saw that if you want to extract a hyperbolic space out of your cube complex where your group acts, you also do so via hyperplanes. So anything geometric group theory type that you want to do in a Cat-zero cube complex can be done via hyperplanes. That's the summary of the story. And what I want to tell you now is that you can do this. You can do this elsewhere. So for the next two slides, I'll be a little bit informal, but I'll tell you where I'm being informal. So take a geodesic metric space F, and suppose you have a map from your geodesic metric space X to R. And let's say that your map is a contraction. It decreases distances, but maybe not decreases distances. Maybe it doesn't just decrease them on the nose. Maybe you have like some error of a uniform K. That's fine. I'm also going to think of that as a contraction. Okay. So I have a map, which is a contraction. Maybe it's a coarse contraction. All right. And suppose that the map satisfies the following. It satisfies that the fibers of points are convex. And of course, you want to ask me, what do I mean by convex? And this is why this slide is informal. It's because the word convex is going to change its meaning based on the space that you live in. Sometimes it's going to actually mean convex, where any 2 points in the set are connected via a geodesic that lives in the set. But sometimes it might mean quasi-convex, where any 2 points in the set are connected via a quasi-geodesic that, So when we see examples, we'll see what the word convex means. But the idea is that, so the definition here is that I have a map from X to R, it coarsely decreases distances. And if I look at fibers, if I look at the fibers of this map, of the pre-images of a point, maybe, I look at the pre-image of a point, then this pre-image is going to satisfy some convexity property, okay? Ideally, you want to say strict convexity, but maybe you'll have quasi-convexity. But that's the idea, okay? Now, what I'm going to refer to such a map by a convex contraction. It's a contraction because of this condition. It's convex because fibers are going to be convex with respect to some notion of convexity. Now, something that's immediate from this definition is that anytime you have something of that form, so you have, what do you have? You have a map that goes from X to R. It's a contraction, so it's continuous or coarsely continuous. We don't care, but you have a map that goes to R, all right? And fibers are convex. So there is something that you can do. You can take a point and take the pre-image of it, all right? And this defines you a hyperplane. I'm defining a hyperplane to be the pre-image of a point here. And it is going to be a hyperplane in a very meaningful way, right? Because this side is going to project here, and this side is going to project here. And there is no way, any path that goes from this side to this side must cross the hyperplane by the intermediate value theorem. Namely, if something projects here and something else projects here and take a path between them, you have to have something that projects, to P. So what's the idea? The idea is that anytime you have something like a convex contraction, there are natural hyperplanes associated to it by taking the pre-image of a point, or maybe the pre-image of an interval. If that suits you better, the pre-image of an interval also plays the role of a hyperplane, because again, there is this side and there is this side, and there is no way to go from here to here without crossing the pre-image. Okay, so now let's add one more layer to this definition. So a space X is said to be witnessed by contractions if there exists a constant K such that for any 2 points X and Y in the space, there is a convex contraction that sends them approximately their distance away. Let's take a second to parse what this is saying. This is saying there is a constant K that's uniform, depends only on the space, where for any 2 points X and Y in the space, you can find a convex contraction to R. You can find a map to R, which is convex contraction, where the image of X and the image of Y are coarsely their original distance away. All right. So that's what this is saying. This is saying that the image of X and the image of Y, they can't shrink by much. We already knew that they can't expand by much because we're saying it's a convex contraction, right? Anyway, so the point is, you want a uniform constant where for any points X and Y, you can find some convex contraction to R that sends them approximately their distance away. Okay. Now, so let's try to think of examples where this thing here is met, just to make sure we're not talking nonsense. So let's maybe look at Z plus Z, and we take. Now I will insist on some participation. So let's maybe take this point 0, 0, and this point, I don't know, 5, 0 or 3, 0, something, 1, 2, 3, 4. Okay, and the question is, so I just handed you 2 points in Z plus Z, and I want to ask, can you find me a convex contraction that sends me approximately the distance away? And now I will make convex precise. I want to be convex with respect to the L1 distance, okay? So I want, I'm taking Z plus Z with the L1 distance, just a combinatorial distance. That's the only distance for me. Yeah. I'm taking Z plus Z with a combinatorial distance. And so convexity is combinatorial convexity. So a set is convex if for any 2 points in it, any combinatorial geodesic connecting them remains in the set. So my question is, I hand you these 2 points. Can you think of a contraction, of a convex contraction that sends them approximately their distance away? Do you want to try something? Just try to do something. Any shot? Okay, so what you can do, you can just do the nearest point projection in this example. You can just do the nearest point projection to the interval 0 up to 4, and you can convince yourself that fibers are going to be convex, and that fibers are actually going to look very much like hyperplanes here, and that's going to be a convex contraction that sends them exactly their distance away. So let's maybe change the game a bit. Let's say instead I will take. Instead, let's maybe take the point 0, 0, and I'm still in Z plus Z, but maybe I'll take 3, 3, or I don't know, this is 5, 3 or something. Now, can you think of a convex contraction that sends these 2 points approximately their distance away? You can try to say, well, I'm going to do the nearest point projection to this geodesic, but that's not going to be a contraction because it's not going to even really be a map, because you'll have points here that will have two different images. Okay, so what you can do here is, instead of doing the nearest point projection to the entire geodesic, you just do the nearest point projection to this piece here. In other words, what you do is that you look at the largest chain of hyperplanes that separates. You look at the largest chain of hyperplanes that separate these points, all right? And then maybe you take a geodesic that crosses all of them and you project to that geodesic. And that's going to give you a contraction that sends the 2 points approximately their distance away. That's the idea. Okay. Okay, so let's see some examples where this property holds. If you take, and by this property, I mean, for any 2 points, there is a convex contraction that sends them approximately their distance away. Let's take a hyperbolic space or a hyperbolic group. All right. If I hand you 2 points in a hyperbolic group, can you think of a convex contraction that sends them approximately their distance away? You can just do the nearest point projection to that geodesic. That will stabilize X, will stabilize Y, right? And the reason it's going to be, well, it's going to be a contraction by just projections to geodesics and hyperbolic spaces, they're coarsely contracting, and so fibers are going to be convex. Why will they be convex? Well, let's see. So take 2 points P, and so let's say that. Oh, what happened? Yeah, sorry. So let's take some pre-image of a point here P. So here is P, and let's take its pre-image under the nearest point projection, and maybe I'll take a point P prime and a point P double prime that live in the pre-image. I don't know what's going on here. Okay, so what I did, I took a point P between X and Y, and I took P prime and P double prime that live in the pre-image. And what I want to convince you with is that this pre-image is convex. Namely, if you take a geodesic that connects these 2 points, right? Because of hyperbolicity, this geodesic has to be contained in the union of this geodesic and this geodesic, right? But both of these geodesics, this one and this one, they both project to P, because P prime projects to P, P double prime projects to P. And this geodesic here is essentially contained in their union, so it's also going to project to P. So that's why this is a convex contraction. Now, more generally, in a ket0 cube complex, so this is so what I have just maybe shown you is that if you have a hyperbolic group, then any 2 points in the hyperbolic group, for any 2 points, you can find a convex contraction that sends approximately their distance away. Now you can do the same for a ket0 cube complex, right? So if I hand you a ket0 cube complex and I hand you 2 points X and Y, you just look at the largest chain of hyperplanes that separate them. So you look at the largest chain of hyperplanes that separate them, and then you define a contraction as follows. You just say, well, I'm going to send this entire half space to this point, all right? This entire hyperplane to this point, this entire half space to this point, this entire hyperplane to this point. And what you get is a map that sends X and Y, the number of chain that separate them. It sends X, if they're separated by a chain of 10 hyperplanes, this map sends X and Y 10 away. And the map is convex, just by the way I defined it. The fibers, I sent everything here to a point. I sent this entire hyperplane to a point, this entire piece to a point, right? So the fibers of this map are going to be convex just by the way I defined the map. Okay, so now you take a ket0 space. Well, what can you do? Well, in a ket0 space, you have something very nice, which is the nearest point projection on any geodesic. So if you take X and Y and you take the ket0 geodesic, connecting them, okay, you define a map. You can define, you just take the map. Maybe I'll call the geodesic B. So B is the geodesic that connects X and Y. So take the map that does the nearest point projection to this B, all right? Now this map is going to be a contraction. That's known that nearest point projections to geodesics are contracting. However, it's not going to be, so the notion of convexity is going to satisfy is the following. If you take a point here, maybe I'll call it P, and you look at its pre-image under the nearest point projection, all right, so maybe its pre-image looks something like this, then surprisingly enough, this set is not going to be convex. There are counterexamples. So if you look at the pre-image, this set is not going to be convex, which is pretty weird. I mean, what this says, it says that you can have 2 points A and B, both of which project to P, but the geodesic connecting them does not. And so this does happen. However, this fiber is going to satisfy the following convexity property, which is called star convexity. The points P here is going to be connected by a geodesic to any other point in the hyperplane, right? If you give me any point A that projects to P, then the entire geodesic connecting them must also project to P, right? So the fibers are going to be star convex, and that turns out to be good enough for the things I'm going to talk about. So another class of spaces that satisfy this property is HHGs. And maybe, so maybe I'll give you the idea of how that works. Well, HHGs, they already come with a family of hyperbolic spaces, right? You have the CS, you have the CU, and then and they come with maps by to each of these hyperbolic spaces. Okay, so you have a map by U, and what you can do, well, you just take a geodesic here, all right, and then what you do is take a point that lives in G, map it here, and then do nearest point projection. All right, so this gives you lots and lots of maps because so you do this, you take every line in the curve graph. Okay, so here is the curve graph. You take every line in the curve graph and you build a map out of every such line, and you do it by going from G to the curve graph and then just projecting, doing the nearest point projection to that line. And each step of this map is a convex step, because the map by S is not just any map, it's a distance decreasing map which coarsely preserves median. And preserving median, it essentially says that fibers are going to be convex. So you do this here, and you do this for the CS, you do this for every possible hyperbolic space, and you get lots and lots of you get lots of maps to and then the distance formula will tell you that for any 2 points X and Y, you can find a convex contraction that sends them approximately their distance away. But that's the idea. The idea is that you can just exploit things like the nearest point projection to get hyperplanes in a meaningful way. Okay. Okay, so let's just focus on cat zero spaces from now on. So let's take a cat zero space X, and let's take a geodesic B that lives in the cat zero space X, and let's take the nearest point projection from the space X to B. Okay, a curtain dual to B, by definition, is the pre-image of an interval of length 1 inside B. So I have my geodesic B. All right. What I'm defining to be a curtain is I take an interval of length 1 inside B, and I take the pre-image under the nearest point projection. So your curtain is going to look like this because the maps are distance decreasing, and the smallest the distance can be, it happens here at the end of the and as you can see, this splits your space into, well, it splits it into 3 pieces, right? You have, maybe you call this H minus, you call this H plus, and then this is H. But and if you have a point here and a point here, then you have to go in between. So all the hyperplane properties go through. Something that's worth pointing out is that the distance between 2 points here is coarsely the cardinality of the largest chain of curtains that separate them. Well, why? It's because if you have 2 points X and Y that are at distance 10, you can easily find a chain of 10 curtains that separate them. How do you do it? Well, just take the pre-image of this geodesic, of this, take the pre-image of 0 up to 1, take the pre-image of 1 up to 2, etc. And the larger the distance is, the larger such hyperplanes there are. So this shows you that if the distance is large, this shows you that these two quantities, they're actually the same up to 1. Okay, the distance between 2 points is the cardinality of the largest chain of curtains that separate them. Okay, so here is so one thing that we prove is that the contracting notion, a geodesic ray being contracting, the same way it's described via its itinerary with hyperplanes and cube complexes, it's also described via its itinerary with curtains in cat zero spaces. Namely, a geodesic ray is decontracting if and only if it crosses an infinite chain of L-separated curtains at a uniform rate. Okay. Okay, so let's now talk about hyperbolicity. So take a ket0 space X. So X is a ket0 space. And we're gonna build a hyperbolic space out of it as follows. You define, so take X and fix L for now. Okay, so define XL to just be X, all right, just be X, and define the L distance between 2 points X and Y to be the cardinality of the L chain, the cardinality of the L separated chain that separate X and Y. Basically the exact same thing we did in the ket0 cube complex. Okay, so this, maybe I'll go back. This observation here, it says that the distance between 2 points is the cardinality of the chain that separate them. What we're saying is that instead of taking every hyperplane in the chain, only take the ones that are L separated. Okay, so you fix L and you define it to be the cardinality of the L separated chain that separate X and Y, and you add one for just to make some some triangle inequality work. You should just ignore this one. Okay, so what do we prove about these XL? So we show that each of these XL is going to be a hyperbolic for some L. It's a quasi-geodesic metric space. Any 2 points are connected by a uniform quality quasi-geodesic. And if G acts co-compactly on X by isometries, then it will act co-boundedly by isometries on XL. And this point is obvious because this XL is the same as X, but the distance is smaller, right? So if you acted co-boundedly on X, you better act co-boundedly on XL because it's the same set. It's just the distance got smaller. So what do we also have? So an element G. So one of the things that we'd like to understand about ket0 groups is when does a ket0 group contain a rank 1 isometry? And this theorem here, it gives you a characterization of when that happens. Namely, an element G is rank 1 if and only if it acts lexodromically on one of these XLs, if and only if it skewers a pair of separated hyperplanes. And the third item here, well, sorry, this should be curtains. The third item just means, so skewering a pair of separated hyperplanes, it just means that you have a pair of separated hyperplanes. They're L separated for some L. And skewering them just means that you have an element G that moves this hyperplane or this curtain inside the other curtain. That's what it means to skewer a pair of separated curtains. Okay. Okay, so the idea, so the point is we build some hyperbolic spaces where your ket0 group acts on isometrically and co-boundedly if the original action was co-bounded. And we have and the elements that make distance on these XLs are precisely the rank 1 elements in the group. And if the action on X was proper, so if you started the proper action, so here I only assumed co-compact, but if it was also proper, then every rank 1 element G acts as a WPD element on some XL. Okay. Now I'll just mention one more what I think is an interesting consequence. So in Capris and Sageev, they proved that. Okay. In geometric group theory, what do we like to do? We like to go back and forth between geometry and algebra. And one of the theorems in Capris and Sageev states that if you have a group G that acts co-compactly on a ket0 cube complex, then if your ket0 cube complex contains 2 separated hyperplanes, it must contain a rank 1 element. So it describes the existence of rank 1 elements purely via the existence of a geometric property, which is the existence of 2 separated hyperplanes. And this theorem, it provides you something similar. It says that if you have a co-compact action on a ket0 space, okay, I keep calling them hyperplanes, but we decided to call them curtains. So this is curtains. So if you have a co-compact action on a ket0 space, okay, which has the geodesic extension property, then the group G contains a rank 1 element if and only if there exists 5 pairwise L-separated curtains. What this says in terms of the XLs, okay, this says that each XL has, so this says that each XL has diameter at most 6, or G contains a rank 1 element. And maybe I'll stop here and I'll take questions. I'm not gonna. And thanks for listening. Oops. Yeah. Sorry. Thanks for listening, and yeah, I'll stop.
Okay, thank you. Thank you very much, Abdul. That's great. So are there any questions for Abdul?
So if you start with the Euclidean space, what's the XL do you get?
If you start with what?
Euclidean space.
You get nothing. You get like a point, a space. Yeah, you get. I mean, the set is going to be the Euclidean space is a set, but the diameter is going to be like 1.
Okay.
And if you start with something hyperbolic, you'll get that. If you start with a hyperbolic cat-zero space, you'll recover the hyperbolic cat-zero space. I mean, you have lots of XLs, but if you start with a hyperbolic space, after a certain L, they'll all stabilize and they'll all just be equal to what you started with.
Any other questions? Okay, maybe I'll ask something. I probably kind of missed it. So how does this coincide with the curve graph?
Yeah, so this is, yeah, so that's a good question. So right, so okay, like there is one, so I structured the talk to focus on the category of cat-zero spaces, but you can play a similar game with HHGs. How do you? Maybe I described I described the game vaguely. So maybe I'll go to if you have, yeah. So maybe we'll go here. Okay, so okay, so what do you wanna say? You want to say that you want to define hyperplanes and HHGs. So here is what you do. You first define hyperplanes and HHGs. And how do you define it? So you take your HHG, or say mapping class group, and then you take the curve graph. Okay, and then you take every hyperbolic space that nests in it. All right. So now what you can do, you can pick a line here and look at the projection pi s, and then compose it with the nearest point projection to this line. You get a map that goes to the line, right?
Mm.
Fibers of this map are going to be, you can take fibers of this map and call those hyperplanes. Fibers of the composition, you go pi s nearest point projection, and then take fibers, and you get lots of hyperplanes in your G. Now do this with every line in CS. So we did that with one line. Just pick another line and play the same game. Do pi s, do nearest point projection to that line. You get lots and lots of hyperplanes. Okay, and then do that for every other hyperbolic space as well. Pick a line in some other hyperbolic space, in some other hyperbolic space that comes from a subsurface. Pick a line there. Do pi s nearest point projection, and then take fibers. You'll get lots and lots of hyperplanes in your space. And the distance formula will say that the distance between 2 points is the largest chain of hyperplanes that separate them. If you think about it, because you're either going, if you're making distance, you have to be making distance somewhere, and the distance that, let's say that you're making distance in CS, you're going to be crossing the line that you took the nearest point projection of, which means you'd have to be crossing these hyperplanes. So okay, so the point is, I just told you how to build hyperplanes in G. Now you define the distance the exact same way we described. You say, I'm gonna define the distance on G to be I'm going to count the number of separated hyperplanes, and that recovers the curve graph.
I see. So for example, you get the distance formula the same way if you were to try to get the distance formula.
I'm not sure what you mean.
Yeah, so the distance between 2 points, like, or two group elements. So you can do this through the marking complex, or I mean, which boils down to the formula Maser-Main's case, or the HHS one, I guess. Same. So yours would give the ultimately the HHG, the one coming from the HHG hierarchical hyperbolic structure.
Yes.
Okay.
Yeah.
Just a different way of seeing. I was wondering if you had like made a different complex out of all of this data.
No, it's basically we make so that if you go back to Genevious' definition, it makes sense anytime you have something like a hyperplane. That's the idea, or that's the upshot of this project, is that if you have anything that separates the space, you can build something similar. And what I'm saying about recovering the curve complex is not really so deep, because I'm taking the curve complex in the first place, and I'm just defining fibers to be the nearest point projections to that line in the curve complex. So you get that's the idea.
Okay, it's not like discovering the curve complex all over again.
No, yeah. No, I mean there is an interesting theorem due to my collaborator Harry. Like it's a recent thing. He showed that the mapping class group is quasi-isometric to a cube complex. Like it doesn't act, but there is a quasi-isometry between the mapping class group and some Cat0 cube complex, and it's a median quasi-isometry, so it's more than just a quasi-isometry.
I see.
Yeah.
Okay.
Yeah.
All right. Great. Thank you.
Thanks.
Okay. Are there any other questions from the audience? Well, I guess that's it. Well, thank you so much for joining us.
Yeah. Thanks for inviting me.
And thanks for everyone also showing up at this relatively early hour. All right.
Okay.
Well, bye. Thank you again.